psi2 dot is psi3, and so and so. And the control law star gives you that psi r dot is v, right? Which in linear form, this is 0, 1, zeros, 0, 0, 1, zeros, so and so, and the last row is just zeros. The eigenvalues are zeros of this system, but it doesn't matter because I can design V to place the poles wherever I want. So this is psi, and this is zeros 1, the last entry V. Okay? Any questions so far? In this case, we call the system, we say the system has a relative degree R. So definition, the system 1, which is, we're going to refer to it several times. This is just for your sake. This is the system 1. We're going to play with it throughout the entire lecture. Single input and single output, but it can be many states, it doesn't matter. The system 1 has a relative degree. So this is the definition is for the relative degree. A relative degree R, which is typically less than or equal to n, at some point x naught in the manifold, if this lead derivative, which is the coefficient of the output, the coefficient of the input, sorry, so this is r minus 2. This is actually over there. H is strictly 0, I is all these guys are r minus 2, and the r minus 1 thing is non-zero, and these for all x in some neighborhood of x naught. Okay? So this is, if we have this, we say the system has a relative degree R, and then we can do input-output linearization. Any questions so far? Any question? Let's give a super simple example on the relative degree to illustrate the idea of the relative degree. So we have, this is a mass spring damper system. So the position dot is the velocity, second state, the velocity dot is the acceleration, here is the spring force with unit spring, unit mass, the damping force, unit damper, damping coefficient, unit mass. And I will add a nonlinear spring, so with nonlinear spring term. There is your force, okay? If you have a question, please stop me. Okay, so the first case, let's consider your output to be just x1. Okay, let's consider the output to be x1. So please differentiate your output. So it's x1 dot. So this is x2. No u here, no coefficient of u. So I'm gonna go and differentiate again. So now y double dot is just x2 dot, which is negative x1, negative x2, x1 cubed plus 1 times u. So this guy is not 0 for all x. So the system has relative degree 2, right? So differentiated twice, the relative degree 2. Okay? And the system is order 2. So actually this is input state linearizable, which is obvious from the beginning because the only nonlinear term appears here right next to u, so I can cancel it by choice of u, right? So if you choose another output, remember the output, you may not always have luxury to choose the output you like. The output is the thing that you can measure, right? So this is pretty much is dictated upon you, but sometimes you have freedom to choose the output. So if your output is x2, say, okay, so my output dot is x2 dot, which is the same equation, and the input appears immediately, so the relative degree is what?
1.
Is 1. Very good. So I have one linear equation and the remaining dynamics I have no clue over, maybe linear, maybe non-linear. Let's say the output is some function of x2. So that's okay. So this is negative sine x2, x2 dot. So it's negative sine x2 times this guy. So the coefficient of u, I have here plus u. The coefficient of u is negative sine x2, right? Which is 0 for all x2 that is in the pi. N is integer. Yeah. So if we're, in particular, if we're interested to work around the origin, like always, this system doesn't have a well-defined relative degree because when we ask that the coefficient of the input vanishes, it should vanishes completely, not just at a point. Okay. So here, so the input should not appear like in the first case. Look at the first equation. Y dot is just x2. There is no input whatsoever. Here there is input dependence, but the dependence itself may vanish at some points. So if you work near these points, if you work near at any neighborhood, near any neighborhood of these points, then the relative degree is not defined. But here the relative degree is not well defined at all x's with x2 is in the part. Okay. So we cannot do input-output linearization with this output function. Okay? So some conclusions about the relative degree. The relative degree is the number of differentiations, right? You keep differentiating your output until what happens? U appears, right? With a coefficient that doesn't vanish in a neighborhood of the point. Obviously, the relative degree depends on the choice of the output, right? In this sense, actually, the input state linearization, if you want to linearize the entire system, it's as if you're looking for some function, right? Looking for some output function such that the relative degree is what? N, very good. Yes, the relative degree depends on y, but for fixed y, if you fix your output, the relative degree is actually invariant. If you change the coordinates, if you did feedback, it doesn't matter. It's a relation between the input and the output, doesn't depend on the representation, the internal representation. Okay? So my question to you is, this concept of relative degree new to you? I mean, the word at least. Did you ever hear relative degree before? So I'm reminding you, for linear systems, for example, so we have a transfer function here. So this is bms to the m, b naught, and here s to the n, an minus 1, sn minus 1, a naught. So this is degree n, this is degree m. Obviously, n is larger than m here. What is the relative degree for this transfer function? What was the relative degree? Did you remember? What is the relative degree of a transfer function?
N minus m.
Yeah, n minus m, right? The number of poles minus number of zeros, right? This is actually n minus m. And so let's relate it to the concept that we just learned. We said the relative degree is the number of differentiation of the output until the input appears. So let's check if this is the case here with this definition. So actually the concept of relative degree carries over from linear systems. Let's do some realization of this guy, and let's assume that it's minimal realization. So I have x dot equals ax plus bu, y is cx, okay? Without loss of generality, I can choose the A to be the controllable canonical form, Why without loss of generality? Because we just said that the relative degree is invariant. It doesn't matter how you represent your system. So I will choose it to be 0, 1, 0s, 0, 0, 1, and so until here is 1, and the last row is just these coefficients, negative a0, negative an minus 1. The b is zeros, and the last element is 1. The c is these guys, b0 up to bm, and the rest should be zeros because you don't have coefficients. So this is r minus 1 zeros, okay? That's okay. Let's differentiate the output. Y dot is cx dot, so it's cax plus cb times u. Let's multiply c and b, please. Well, the only non-zero element here is the last element, and here it has 0, so actually this guy is 0, right? So keep differentiating. Y double dot is ca squared x plus cab times u. Well, what about ab? Let's get ab. If you multiply a and b, because the row before the last has 1 here, will be multiplied by the 1 there. So the 1 in b will be shifted up once. And you will have something. In particular, you will have negative a minus 1 or something. It doesn't matter. And actually also, if you multiply again by a, every time you multiply by a, this one moves up. So you have zeros. Now